Right, we're going to kick off chapter 2 here with a little introduction to just some various types of functions that you guys are all familiar with, and then we're going to have a focus on quadratics. So first page, this is just about identifying a couple names, make sure we're all familiar with. Polynomial function must have positive exponents. In order to be a polynomial function, and the coefficients must be real numbers. So let me take you through just a couple differences here for which ones would qualify or not qualify. So here's in a nutshell a little bit of what we just talked about. So if you look at a case like part A and part D, those would be polynomial functions because they do fit the description that we just talked about. Part B is not a polynomial function because of the negative exponent. And then part C is sort of a little bit of a unique case, but this guy could not be put into a polynomial form. And that actually is what I'm going to show you right now. So I filled out a little chart, a little open-ended chart on the notes here that we're going to go through, but this is where it's coming from. So there's a blue box in your book here that we're going to fill out in this little chart in the notes, but you got the zero function where it's just like y equals 0. The degree of a polynomial is the biggest exponent. So if you look at the zero function of f of x equals 0, this does not have an exponent because you couldn't take any value and raise it to any exponent and create a 0 result, right? Even something to the 0 power is just 1. So for this guy, they just say it's an undefined degree. You go down to your constant function, so that's just like y equals a number, right? Like y equals 5 or something like that. So that would be a 0 exponent since there is no x involved. So think of it as like ax to the 0 power. If you have y equals ax plus b, so this is our linear function because this would be x to the first. So that's why it's a degree of 1. And then of course the quadratic is x squared, so it's a degree of 2. So I'm going to throw those into our little handout that we got going on down here, and then we'll move on to the next page. So I just wanted these in here for your notes so you at least had them. So I'm trying to pull out some of that important information that I want you guys to hang on to. So this was our f of x equals 0. And then again, they had an undefined degree as far as exponents go. The leading coefficient wouldn't exist. We're not going to fill out all the leading coefficients. The leading coefficient is just the value in front of x, the x with the highest exponent on it. As far as the constant function goes, we would just say the book has f of x equals a. Right, so that just means a can represent any real number. So like y equals 3, y equals 4, y equals 5. Those are just constant functions. Those are just straight lines, like horizontal lines. The degree on those would be 0. Right? If you think of it as, like, let's just say you have the line y equals 4. So if I have y equals 4x to the 0 power, that is the same thing as y equals 4. Right? So those are our constant functions. Linear functions is where you have x to the first. So we're going to say f of x equals, we'll put the whole ax plus b in here. So you can always think of this as y equals mx plus b, same thing. So those are our linear functions because they are x to the first. So that's why they call it a degree of 1. And then your quadratics, the general form on these guys that you guys already know, ax squared plus bx plus c is our general form for the quadratic. Highest exponent's a 2, so we call it a degree of 2. And of course the list continues with higher and higher degree functions, but we're going to pause on that one right now and jump to the next page. So just finding the equation of a linear function. So they're giving us some values right here. So that when they say something like f of 3 equals 3, so just remember how we would interpret that. They're saying if I plug in 3 for x, the result, or the y value, would also be 3. So it's like they're giving us an ordered pair. When they have f of 5 equals 8, that means when I plug in 5 for x, the result would be 8. Right? So they're giving us something like this. As far as writing the linear function model in just of a form like y equals mx plus b, first thing we always do is solve for slope. So you guys remember your slope formula. So y minus y over x minus x. So I'm just taking those numbers right there, and we're just doing the 8 minus 3 over 5 minus 3. And so that's giving us our slope. From there, we're going to use our point slope formula. Right? So we have a point, which is the x1 and y1. That's a point, and that can be either of these points. We also have m, which is our slope. And so we're going to use all that to do a little cleanup and figure out what is the y-intercept so that we can write it into this form right here. Okay, so they plugged in the 0.33 for x and y. So there's my x1 and my y1. We plugged in the result that we just got up above for slope. That's our m. So this is our linear function in point slope form, but I would only have you guys leave it in this form if the direction specifically said. Typically, we're going to put these into an ax plus b or mx plus b form, however you want to say that. So they're going to distribute that 5 halves, and then they're going to add this 3 over in order to put it into sort of a proper format here. So this is kind of the go-to form unless the directions say otherwise. So we are going to do a little side work on our own down here, since you guys have seen that. Slope ultimately is going to lead us into derivatives, which is like our major concept, one of our major concepts in calculus. So we're going to introduce that idea over here so I can kind of give you that connection. So let's just try what we just did up above. So if we had f of 2 equals 3, again they're saying if I plug in 2 I get 3 for the y value, and then next to it f of 6 equals 3. So if we plug in 6 for x, we get 3 as the result. So we're going to start out by finding our slope. So we're just going to do a little y minus y over x minus x. And you can see based on the numerator that we're going to get 0. So this is kind of one of our special cases. So if our slope is 0, what kind of a line is that? That would just be a horizontal line that has a slope of 0. Remember, if you get 0 on bottom, then it's undefined, and that would be a vertical line. So, but a horizontal line has a 0 on top, so the result is a 0 slope. As far as just getting the equation of the horizontal line, right? A horizontal line is always just y equals a number, and you can already tell based on this information what that's going to be. But let me just kind of go through the point slope form real quick. I'm going to just pick this first point. So I'm going to do y minus y1 equals my slope times x minus x1. And so you'll see if I distribute the 0, then all I have is 0. And if I add that 3 over, we get the equation of our horizontal line, which is, we already pointed out, based on what I see here and here, I can already tell it's going to be y equals 3. So let me give you one more over here where we'll actually get a sort of a little more of a normal linear function rather than a horizontal line. So again, I got those same points, so we're going to start out with our slope. And we're going to do y minus y over x minus x. So we're getting a slope of 4/3. We're going to plug, let's take the easy information here of -1, 0 to plug into our point slope formula. So I'm going to say y minus y1 equals my slope times x minus x1. This will be a little easier because of the 0 right here. That's just going to be y. On the right side, we're just going to distribute that slope. So we get our 4/3 x plus 4/3. And that would be our function. Okay, so here's the connection that eventually we're going to lead into with calculus and getting into derivatives. I'll show you a little bit of the connection here. So remember, as far as slope goes, it's just an average rate of change, right? That's why we have the y minus y over x minus x. It's just the rate of change. So here was our slope formula that we just went through. We know oftentimes we can use f of x instead of y. So oftentimes it's going to be written this way instead. these x's represent two different x values, right? So whatever they are, in this case, they're just calling them b and a instead of x and x, just to identify the difference between the two. So we can give them two different letters. So we're going to often see it written this way. When you talk about the difference in your y's over the difference in your x's, one of the Greek letters that is often used for a difference is the Greek letter delta, which looks like a triangle like this. So sometimes instead of saying the difference in your y's, they say delta y over delta x instead of saying difference. And then that leads us into this notation. So instead of the delta, oftentimes we're just going to see a d. So if we have dy over dx, and this is the notation that we use for a derivative, right? They call it dy over dx. So ultimately, all this is the idea of a derivative is simply a slope or a rate of change. Okay, and so that's all this is going to come back to this down the road. This is also known as the difference quotient. So remember what a quotient just means division, and difference obviously means subtraction. So when we say the difference in your y's over the difference in your x's, that is a difference quotient. So all that's going to connect down the road. When it all leads back into this idea as we get into calculus. So a little more what we're going to be looking at here is just transforming quadratics. So here is our basic parent function for quadratics, just the y equals x squared. So we've already talked about all these in chapter 1, so wanted to throw that into this model since that's what we're kind of dealing with right now in this first lesson. So a couple reminders here. So if we're going to shift left, we're going to do a vertical shift up 1, and then we're also going to throw in a reflection over the x-axis. So what would that look like if we threw all three of those into this parent function? So as far as shifting left 3, we know the x plus 3 is going to cause that to happen. If we're going to do a vertical shift up 1, remember anything that goes left and right needs to be attached to x. Anything that goes up or down is not attached to x. So if we're going to go up 1, that's something we put out here separate where it's not attached to x. And then the reflection over the x-axis, right, that would cause you to go up or down if I'm going over the x-axis. So again, anything that is up or down is not attached to x. So we're going to put the negative out here, outside the parentheses, not attached to x. And so that's what that would look like. So throw in one with our vertical stretch of 3/2, and then a vertical shift of down 2. So we still have our x squared. So our down 2 is going to play out just like this one did. We can put the whole little minus 2 at the end here. Our vertical stretch of 3/2 just becomes our leading coefficient and would look something like that. And then just a reminder, if this was supposed to be some kind of a horizontal stretch or shrink, remember the horizontal stuff always does the opposite of what you would expect it to do. So like for example, when we went left 3, in here we have plus 3, right? Even though we think of positives as going to the right, as we've already talked about before. So if you were to look at this, if we were going to do a horizontal stretch or shrink, I would have to not only wrap this in parentheses so that it would be attached to x, but I would also have to do the reciprocal right here in order to affect it horizontally. So anyway, jump down to these guys. So our two basic forms that we're going to look at for our graphing functions. Here's kind of the standard form. This is what we call vertex form. Vertex form is probably a little friendlier than this because when you look at it, the h and the k make up the coordinates of your vertex. So this is a pretty friendly form to put things in. This is more closely related to those transformations that we just did up above. They tend to be in this format right here. So when you go to find a vertex for something that's in standard form, and I know you guys have all seen this before, remember that the x coordinate of your vertex, we use negative b over 2a. And that value that you see right here for x equals negative b over 2a also gives you the equation of your axis of symmetry. Right, that axis of symmetry is that vertical line that runs right down the middle of your parabola. So keep those two in mind. And jump over to here. So on this one, if we have something in standard form, This one was asking us to find the vertex and the axis of symmetry, but they also are going to have us write this in vertex form. So they're kind of wanting it all on this one. So first things first, we can, just based on that information, we can do our negative b over 2a in order to get the axis of symmetry. And that axis of symmetry, that value of 1, if we just plug it in, the result of that gives us the y-coordinate of our vertex. So this gives us the x-coordinate. Plugging it back in, the result gives us our y-coordinate. So if we put those values together, we have the point of our vertex. As far as rewriting this into vertex form, once you have this information, you can take this and then just put it into that vertex form. So I showed you on the last page. Let me just put it here so we can see them side by side. So I know the 1 and the negative 4 are going right here for h and k in order to give us that part of it. What about the a value? So if you go back up to here, you can see our a value was, oops, sorry, these were in not the right order. Our a value was right here. It was positive 1. So I can put a 1 right there for my a value, and that's where they're getting this set up. We can use completing the square as well, but one option is to, if we use this process first, is just to take that information to help put it into our vertex form. So let's give one of those a try. So first things first, just like the one up above, let's put this into the proper order before we start finding information with it. So we always want the x squared to come first. Our highest degree needs to be our leading term. So we have our x squared minus 6x plus 2. And so first things first, we're going to do our negative b over 2a. So negative b over 2a is going to give us our axis of symmetry, which is x equals 3. Do keep in mind that if you're ever asked on a test question to write the equation of your axis of symmetry, it does need to be an equation. So we need to write it as x equals a number. It's never just a number, right? It's a line, it's not a point. So we always write it as an equation. So there's our axis of symmetry. If we take that 3 and sub it back in for x right there and right there, we're going to get our y-coordinate to complete our vertex. So I'm going to say, we could have done it from here as well. I'm just going off of this because that's what I was looking at. So I'm going to put my 3 in for x in both places. And we'll do a little cleanup on that. So 2 minus 18, so negative 16 plus 9 is going to give us negative 7. So there's our y-coordinate. So we have all the pieces now in order to write this into vertex form. And so we can now do this actually without having to complete the square to do this. So I can plug in my 3 for h, my negative 7 for k, and I can see right here that my a value was 1. And so that's just going to be a value of 1. And so if we throw it into that scenario, then we have our same function, but this one's in standard form. This guy would be in vertex form. So jump on down to this one. So now they're asking us to use completing the square. So this is really just sort of a different method, a different way of getting there. So I wanted to remind you guys what that process looks like. So we're going to work through this one together. So on this one, the idea is I want to create a perfect square so that when I factor it, I would have identical factors. And you'll see how that works here as we go through this. So in order to complete the square, one thing we need first is to get the leading 2 out of the way, because when we complete the square, we need it as just 1x squared. So we are going to, just from the first 2 terms, I'm going to kind of group those guys together. I'm going to factor out the 2 so that it looks like this. leave yourself some space. So we got that 2 out of the way, so it's just 1x squared. And so now we can complete the square on what you see in parentheses. So there's a little formula that you guys have seen in the past when you learned how to complete the square. What do we want this c value to be in order to have a perfect square? Right? This is my a term, my b term, and my c term. So there's a little formula we use to complete the square in order to get that perfect square trinomial. So c is b over 2 squared. And that might ring a bell for you. You guys have seen that in the past. So if I take my b term, which is 2, so if I did 2 over 2 squared, that tells me that I need to add 1 in order to complete the square. So the idea, though, is whatever I just threw into this function, I have to now also subtract it out, because we can't just throw in numbers for fun, because it changes our value. So in order to keep things as they were and to keep this equation balanced, you can see based on this, I essentially just added 2 to our function, right? Because this 2 distributes to everything inside of the parentheses. So if I multiply those together, it tells me I just added 2 to this function, which means I'm also going to take away 2 in order to keep it balanced. I'm doing this, subtracting that 2, simply because it's on the same side of the equation, right? It's not, if I were to add 2 to the right side, I could also add 2 to the left side, but then I would need to subtract it over, right, in order to get f of x by itself. So we can look at it either way. So if we do a little cleanup on this, we have that leading coefficient of 2. This is our perfect square. If you were to factor this, what would your factors be? Right, they would be x plus 1, x plus 1. In other words, we can write that as x plus 1 quantity squared. And then if I clean up the right side here, I have my minus 3. And so that's it for this one. That's how we complete the square, and that's how we use the process of completing the square in order to rewrite it into vertex form. We could have done the same thing up here. We just took a different approach. So this is just another way of getting to that place. So now we could describe it, though, because now we can say, all right, my vertex is -1, -3. I can tell based on this that it's positive, so I know it's going to open upward. This is also my vertical stretch of 2. As far as getting the values for the x-intercepts, which is what they got right here, that we would have to do with either a calculator or quadratic formula in order to get those. So if we were to set, or we could solve it from here, if we just set the equation equal to 0 and solve it, that's how they're coming up with this information as far as finding the x-intercepts. So we're going to try all that on our own here. So feel free to pause this and give this one a try. This is going to be the last thing that we do for this lesson. So if you want to work ahead of me, feel free. So we're going to use our completing the square process, and then we're also going to graph it together as well so you can see how all that should go. So we have 2x squared minus 8x plus 5. So first things first is, if there's a number here in front of x squared, we're going to start by factoring that out. Leave yourself some space. Bring down that plus 5. So we're going to factor out that 2, and then what number needs to go here in order to complete the square. So if we did our c equals b over 2 squared, so I'm going to do my b over 2 squared. If we do a little cleanup on that, that tells us we need to add 4 in order to create that perfect square. So what did we just add to our equation? Right? Technically, we just added 8 to the right side of this equation. So I'm also going to take away 8 from the right side of this equation in order to keep it balanced. And if we simplify that, so if you were to factor what you see in parentheses right here, our factors would be x minus 2, x minus 2. So we're going to write that as x minus 2 squared. Bring down our minus 3 at the end. So we have our setup. So now some of the main things they want us to identify. We can see our vertex is positive 2, negative 3. And I'll write it this way. We could describe this as an upward facing graph. We could say it's got a vertical stretch of 2. The other thing that we could find would be our x-intercepts. So if you want to find those by hand, we could certainly do that. I simply set the equation equal to 0 and solve for x. So first thing that you would do is you would add the 3 over, you would divide by 2. Let me bring that over here. Which would look like this. I could then take the square root of both sides. Which would look like this. And then I could add this 2 over to the other side and get this. And so those would be our x-intercepts. We can clean this up. I know we don't like to leave fractions under the radical. So I could multiply this by the square root of 2 over the square root of 2 in order to rationalize that denominator within our radical. For now, I'm going to leave it just like this. So that's kind of all the information they're asking for. If they want you to sort of back yourself up with this graphically, so let's peek at these guys real quick here. So if we go to our y equals, I'm just going to start with the original function, 2x squared minus 8x plus 5. And I'm going to graph them both right on top of each other just so we can show that our answer was correct. So I'm going to graph this guy as well. So they should line up right on top of each other if we did this right. So we're going to hit graph. So there's the first one. Second one's coming through right on top of it, so perfect match, so we know we did that correctly. If you want to identify the x-intercepts from the calculator, the other way we can do that, instead of solving the equation, if we want to pull them right off of this, remember we go under calc. We're going to choose 0 because these are the zeros of the function. As far as our left boundary goes, let's see, where's my cursor? So there's the first one. So if I want to give it a left boundary, I go a little to the left and hit enter. I can give it a right boundary by going a little to the right of it and hitting enter. And then whenever it says guess, hit enter one more time. And that decimal should match this guy. So if I were to type in 2 minus the square root of 3 over 2, it should give me that decimal. I could do it one more time for the right side, and that decimal should match the plus scenario for this. So if I hit 2 plus the square root of 3 over 2, it should match the decimal that I get from doing it on the right one. And that's it for first lesson of chapter 2.